Okay, hi everyone. I'm Saeed from UNR. Today I'm going to talk about computational IR spectroscopy for detection of metallofullerenes in space, specifically a metal inside C60, and that metal could be lithium, sodium, or potassium. But generally in our research group, we are trying to answer two questions: what is out there and how it got formed. So today I'm going to talk about the what part. Here are some outlines. First I'm going to talk about the goal of this project, and I give you a brief introduction about fullerenes in space and computational IR spectroscopy, and at the end I show you some preliminary results and conclusion at the end. So the goal of this project is to get computationally to obtain IR spectra for these metallofullerenes compounds that I mentioned, but we have to include anharmonicity. And why we are looking for computational spectra? Because these molecules are very hard to purify, and that's why we don't have experimental data available. So we are trying to make or model it computationally. And the reason we have to include anharmonicity, because the studies have shown that the interaction between metal and carbon cage is very weak, and we expect a shallow potential. That's why we have to include anharmonicity in our spectra. And to achieve these goals, we have a few steps to follow. First of all, we have to locate the position of that metal atom inside the cage and find all the possible isomers, and then get the harmonic spectra. And then to include anharmonicity, we need to use time-dependent and time-independent methods. For time-independent method, we used VSCF, or vibrational self-consistent method, and for time-dependent, we use molecular dynamics. This is the telescope. This is called a Spitzer, and this just collects information or signals in IR region, infrared region. And what eventually we're going to do is get our spectra and then compare our results with the data coming from this telescope, and then if they match, we can prove the presence of metallofullerenes in space. And that's how they discovered C60 and C70 for the first time in 2010. Cami and co-workers modeled C60 and C70. This red line is C60. They modeled it computationally, and the blue spectra is C70. And then the black spectra is coming from a Spitzer, so they matched it, and they proved the presence of C60 and C70 in the young planetary nebula, so-called TC1. And a few years later, this Duncan co-workers, they found, they basically proposed that metallofullerenes also can be formed in the same region as easy as fullerenes, and they basically could synthesize sodium inside the cage of C60 by under highly energetic conditions in oxygen and hydrogen rich stellar conditions. And I briefly talk about the methodology I used in the computational IR spectroscopy. I need to be faster. So the very first step is getting harmonic spectra, and when we basically displace the atoms around their equilibrium positions, and we get the force constant and calculate the frequency. This is, as I mentioned, this only includes harmonic frequencies, but we have time-independent vibrational self-consistent method where when we sample energies along the harmonic modes, and we get the vibrational energy levels and wave functions, and we can basically get the overtones, combination bands, and coupling between modes basically. And for time-dependent methods, we have molecular dynamics. There are two codes for that. MD is molecular dynamics, and DRC is dynamic reaction coordinate. This is basically classical trajectory based on the quantum potential energy surface. And we have our initial conditions. We have time and energy we put in the system, and we use Fourier transform of time autocorrelation function to go from time domain to frequency domain, basically. And I know you don't care about these equations, but the first one is the Fourier transform for one trajectory, and the last one is for multiple trajectory when you take average over multiple trajectories. If you have questions later, I can answer, but these are our computational details that we used. Again, you don't care, but so first we got these structures, the isomers of different isomers of sodium at C60. Then in future we're trying to extend it to other metals as well. But this is related to different symmetries of different positions of sodium inside the cage with their relative energies. And this is the first spectra, which is related to harmonic spectra, and the comparison between those different structures. And as you see here, just there is one thing to mention here, that the peaks related to the movement of sodium inside the cage, it has a redshift for C1 symmetry, and this is due to the looser bond of sodium to that structure because of the position of sodium inside the cage. And here I have a comparison between C60 minus and sodium at C60. C60 has only 4 fundamental peaks, but when we have C60 minus, that extra electron which has a resonance inside the cage, can break the symmetry, and we have much more peaks. But you can see the peaks for the the red peaks and the yellow peaks are matched, because we're trying to show here that extra electron or from sodium radical actually transfers to the cage and does the same thing as that minus electron, that extra electron is 60 minus. And we have basically the same peaks except for some extra peaks for sodium at 660, and that's due to the movement of sodium inside the cage. And this is the last result I've got so far for which is a comparison between harmonic and anharmonic, which anharmonic is coming from VSCF. And basically you see here, you see a redshift for anharmonic peaks compared to harmonic ones from the VSCF method. And we also try to use molecular dynamics. First for a simple molecule like water, and that showed us this not only can provide us harmonic or normal modes, but also can give us overtones and combination bands, as you see here. But when we applied this in our system, we could get only lower frequencies, but not higher ones. And we think it's due to the fact that we only used one trajectory, not multiple ones. So we are trying in future to use multiple and take the average over. And as results, IR spectra for these compounds, as I mentioned, are very structural dependent. And harmonic frequencies show the redshift compared to harmonic ones. And in future, in order to sample a complete spectra, we need to, first of all, include the couplings between modes, and also we need to put higher temperature in our system, and also we need to consider multiple trajectory instead of one, and then we can extend our work to other metallofullerenes. Thank you.
Okay, thank you very much for your presentation. I saw you have different energies for different symmetries of metal at C60. Is this is there any? I see your connections with different energies. Is there barriers for this different symmetry?
Yes. I didn't. There is. They have different energies, but we don't know about the barrier, as I showed here in this slide. Okay,
yeah,
this one.
Yeah.
Yeah. The energy difference, so if there are relative energies, but if this is 0, this is 72, and this is 73, but this is what we have found so far. There might be more. I'm trying to find more structures.
Okay.
I guess I was just wondering, so what is the nature of the coordination or the bonding of the metal within the cage? Is it just...
Okay, so the global minima that we have found so far is the sodium is in between, it's closer to the wall, and it is in between pentagon and hexagon. That's the global minima we have found so far. But I'm doing more calculations to find more structures.
Okay.
Yeah.
Thanks.
I'm just wondering how you did the exploration of the minimum configurations of sodium in the bucketball.
Okay. So first I picked some symmetries, C2V, CS, C5V, C3V, and then I did geometry optimization. I found the structures, and I did Hessian calculation at the top of that. If they have imaginary frequencies, I distort them along that imaginary frequency to get the equilibrium or the actual minima. But so far, only these three structures have no imaginary frequencies. So they are actual minimas.
More questions? All right, let's thank the speaker again.